Today, we are talking about conventional ventilation, and then I'm going to roll that into talking about dedicated outdoor air systems, DOAS. And specifically, we'll talk about balanced heat recovery ventilation systems. And I think you're going to find it, although this is a little bit of one of the more tedious chapters that we do get into, because there's a lot of technical, as you'll see, going through the ASHRAE 62.1 calculations for ventilation. It's very much a timely in talking about this. You'll get some insights into the, call it, lack of ventilation or poor ventilation we have in many buildings, because this is what engineers and designers and installers have to go through to try to provide ventilation with conventional unitary systems. And I think you'll find it interesting. So we'll get started, and it's just after noon. And again, if you have any questions, throw them up on the chat. Make sure it's to everyone, and I will try to pick that up. Traditional systems, ventilation methods, rely on rooftop units in a lot of cases, and there are literally millions of these units on top of roofs across the country. And so what you've got is a heating and cooling system that also has a damper and brings in ventilation air, outside air, introduces it into the system, and then that is distributed supply, either heating and cooling with the ventilation into spaces, and then exhaust, return, and it's recirculated. And you might imagine in the age of COVID, right away, that jumps out as maybe not a good idea. Oftentimes there's an exhaust fan or an exhaust stack or multiple exhaust fans, and this can be a little bit of a factor in balance in the building. You're going to depressurize because you've got exhaust here, and if that's not equal to the supply coming in here, and this is just drawn into this system with very simple opening a damper and allowing it to be drawn in, it isn't necessarily on a balanced system. Potentially, you can have a relief fan that is balancing and done by static and provides balancing as well. That is somewhat uncommon in a lot of these systems. And then if you want to add some efficiency, you put an ERV wheel into the system so that the incoming air passes through a heat exchanger and then is introduced into the heating and cooling coils and distributed, and then the exhaust air is providing the heat recovery on the exhaust side. Generally, those are modest in efficiency, and so we have a little bit more limited impact on energy. It helps, but not usually significantly. Now, if we're looking at multiple zones and doing this ventilation, here is just one zone. If you're going into zones, you'll have a supply and exhaust grill, so supply in, exhaust out of each space, and try to do that in a balanced way. And this is where ventilation, when we're calculating the amount of air that's going to be brought into this and then distributed to these three zones, it can be a little bit of a challenge, and that's what we're going to spend a little bit of time here with. It is complicated. It's also extremely difficult to have consistent and correct results doing ventilation this way. So basically what you're doing is taking these multiple zones, and you have to provide these complicated formulas. Don't worry about all this stuff on the page here now. I'm going to take you through this step by step to get some insights into what engineers are doing to try and determine correct ventilation in these spaces. And there are multiple factors that will play into this. You've got ventilation efficiency, is this chart down at the bottom here, and we'll talk a little bit about that. And then you've got your total. So when you go back here, to do heating and cooling, this total amount of air that you're pushing through these supply and return ducts is not going to be the same as the ventilation rate. So you've got to figure out what the percentage of outside air is, and then what that percentage that's going to go into each of these spaces is going to be to determine what your actual ventilation rate is. And so taking it here, we're looking at these three zones. It's a 2,000 square foot office with 20 people. When we talk about primary, that's the actual volume of air to provide heating and cooling and ventilation into that space. So this is going to be getting 2,000 CFM. This is a smaller office. It's going 20 people also. It's going to be getting 1,400 CFM because it's a reduced size office. And then the conference room, which is going to be getting 400 CFM of primary. In other words, primary, again, to remind, is the amount of actual air that that rooftop unit is pushing into each of those spaces for heating, cooling, and ventilation combined. So what you do is you figure out what, as we were doing, determining the ventilation rate, not the primary, but the actual ventilation for fresh air. You take the conference room as 5 CFM per person plus 0.06 CFM per square foot. Turns out the office space is going to be the same, 5 CFM per person, 0.06 CFM per square foot. So if you plug that into these three spaces, we've got 5 CFM times 20 people is 100 CFM plus 0.06 CFM for 2,000 square feet is 120. So this is getting 220 CFM. Here you've got the second office shown the same. And then the conference room is 5 CFM times 12 people is 60 CFM plus 0.06 times 200 square or 300 square feet, excuse me, 18 CFM. So it's 78 CFM of fresh air, outside air. We take this, and then I mentioned the effectiveness. And what this is how effective is the delivery of that air into the room going to be in actually diluting the space with fresh air and exhausting stale air. So this multiplier is based on how effective it's going to be. So if you've got ceiling supply of warm air and it's 15 degrees or more above the space temperature. So if it's 70 degrees in the room, 85 degree air coming in, which would be typical in a minimum for actually providing heat in that office. That's warm air that's coming into the room at the ceiling and a ceiling return. So that air is going to stratify. It's not going to mix and diffuse into the room readily. So it's got a 0.8 multiplier. That means that you need, in order to get 220 CFM of air into that space, you multiply it times, the 0.8, and it's 275 CFM for each of the offices and 98 CFM into the conference room. Now you can see here, this is floor supply of cool air and ceiling return. That means that cool air comes in low. The people and equipment and computers and everything warm that air up, and that air up goes from the bottom, the floor, to the ceiling and is exhausted, and it's going to be very effective. And so you've got a multiplier of 1.2, which means you can use less air to provide the ventilation. In our case here with this office, we need 275, 275, and 98. There's our totals for the volume of air we're moving. The percentage of that, 275 divided by 2,000, you can see this multiplier, that's 0.14, 14% of the 2,000 CFM is outside air. You do the same for the other spaces, and we come out with a ventilation efficiency of 0.9. So now we've got 275 is 14% in this space, 275 is 20% in this space, 98 is 25% in this space. This is going to be a little bit challenging as you start you're probably starting to get a little insight here. In this space, we need 14% outside air, we need 20%, and we need 25%. How do you do that here? So we're going to take and do one last calculation here on how we do this in ventilation. Occupant diversity means that if you've got 2 offices and a conference room, very seldom are you going to have everybody in, your capacity in the office while some of those people are in the conference room. So diversity means that those people are going to spread out in the office. So you've got a total of 40 people, 20 in each office, and you've got capacity for 20 plus 20 plus 12 for the conference room. So you're going to have 52, space for 52, 40 people occupying it. That's 0.77 as far as density, in effect, occupant density in that space. So you take outdoor air supply, apply that diversity, add up all the ventilation we had, so multiply your calculation we had done previously by 0.77. Our outside air requirement is 458 CFM to come through the damper into the rooftop unit and be distributed into the spaces. So the last thing we had was that efficiency of 0.9. That's the last calculation, 458 times our 0.9 for ventilation efficiency. So our total is 508 CFM. Now we look at it in terms of the total volume, 2,000, 1,400, and 400 is 3,800 CFM. 508 CFM of that is our outside air. So our total percentage is 13.4%. So that damper needs to open and provide 13.4% of your primary distribution is outside air. So now we double back and we go back to each one of those offices and we put in that 13.4%, like I was talking about earlier. 2,000 CFM here is 268 CFM of outside air. 1,400 times 13% is 187, and 400 times 13% is 54 CFM. When we first started, we said we needed 275 CFM in each office and 98 CFM in the conference room. So now the conference room is short by 45%, one office is short by 32%, and office 1 is pretty close to being right. Yeah, Caleb asked, you're looking at the heating rather than cooling. Yeah, that's the design is going to be on the heating design for your primary airflow. So I'm using heating because that's it's going to be the worst case. So that's correct, Caleb. So what we're seeing here is the conference room is going to get 54 CFM of fresh air, and it really is calling for 98 CFM, 45% short. Let me ask you, when you have a crisis or you have strategic planning or those critical thinking exercises, where does that usually take place? It's called the conference room. All right, everybody in the conference room, we've got a crisis to deal with. We've got to deal with a problem, or we're going to go in and do some, strategic planning. Let's go in the conference room. Well, that's where CO2 levels now are really high because you have poor ventilation. And we've learned earlier in these workshops that I've been doing that poor ventilation and high CO2 levels lead to cognitive function deficits. And as a result, you're not thinking clearly. So this is very typical in a lot of spaces. And it's going to be, when you're doing a central unit on the roof that's relying on a mix of outside air and heating cooling, you're going to have this varied, accurate number of CFM of outside air to meet your requirements. So it can be a real issue. And it's very difficult to correct that. They have, VAV dampers, variable air volume dampers you can put in rooms and so forth, but it's not an easy fix. It's complex controls and very challenging. And they may work when they're commissioned, but 3 to 5 years down the road, they may not be doing as well at all. So it's really a difficult system. When you start doing dedicated outdoor air systems, it looks a lot different. This is our same zone, but now we've got a dedicated outdoor air system, in this case with heat recovery, and we're bringing fresh air in and distributing into the spaces and exhausting out of the bathroom or exhaust points. You can have grills in the hallway, whatever, but we're exhausting the same amount of air as we're bringing in. And from a perspective of, you may do some tempering, heating, cooling of that air, and it gets pretty simple. The volume in each of the offices is 220 CFM, and in here it's 78 CFM. So you just design your ductwork and use dampers to add those all up and provide ventilation supply into each of those zones very simply. It becomes really easy. So the calculation is almost non-existent. Ceiling supply of cool air or ceiling supply of warm air less than 15% above the space temperature is just a multiplier of 1. And so, generally with very high, especially with very high efficiency heat recovery, you're going to be well less than this 15 degrees. Or you may, in the wintertime, you'd be a little bit cooler, and so it's cool air. So it's basically a multiplier of 1, so standard effectiveness. So guess what? Our system design became really easy. And then other DOAS systems, you can do things like putting your supply air into an air handler in each individual space and then distributing it. We're not big fans of this, but this is done where you would use an air handler from a heat pump system, for example, that does your heating and cooling. It's got a return plenum, and we're providing fresh air into the system and distributing it. And so that's a possibility. It gets a little complex. This is a backdraft damper here. You've got a backdraft damper, and having this air handler and having fans that are drawing air through here are going to have an impact on the static pressure of this supply duct. And so that can have an impact on the balance of the ventilation system for the supply and return air on the DOAS unit. So it's something to just be aware of. And ideally, we like just pushing fresh air into spaces, exhausting stale air, and then doing heating and cooling separately. But we are involved with projects where this is an option, and you just have to make sure that you balance the static when you're doing that. And DOAS allows you to do these things like constant air volume, demand control, or variable air volume, and then applying economizing very simply. Constant air volume is just, you set it and you forget it. You supply 520, you exhaust 520, and it runs. Demand control can be as simple as measuring with a CO2 sensor in the duct on your return air and ramping up and down. Now, as you might imagine, this has some limitations, because if you're getting all your return air here, what's the CO2 level in each of these spaces? You may not really know that. If there's a central return in a hallway, or it's drawing back through the bathroom or another exhaust point, that's going to be the average of all of that return air. So having each individual classroom is potentially a better way to do this. So you put a CO2 sensor in each of those offices or the meeting room, conference room, and a damper opens and allows more air to go in. There are different control strategies on this. You can have a constant static sensor on the supply side, which allows you to sense when this damper is opened, the static would drop. And so the unit ramps up to bring the static back to a set point, and that would be providing more air into that room with open damper. It's a pretty simple but straightforward way to do it. And then you've got also economizing. So what you're doing here is bringing in outside air, and you can route it rather than here with a heat exchanger, it routes it around the heat exchanger, brings cool air typically into the space, and then puts cool air into the rooms to allow them to do some free cooling. And that with DOAS is can be optimized, and you can do up to 100% of the capacity of the ventilation unit. I want to talk about duct design now. And this is really an important component of systems when we're talking about optimizing efficiency. And you can have the best HRV or ERV on the roof. If you do a poor job of designing and or installing the ductwork, you can really cause the fan efficiency on the unit on the roof to be lost because of high static pressure, in other words, and I'm going to talk about specifics that contribute to that. And this is something that my colleague Aubrey and I, a lot of you know Aubrey, know myself, we've seen a lot of things on projects. So I'm going to share some insights on a couple of projects here today. But the ducts are really an important component. And in a lot of cases, when we're doing ventilation systems, the ductwork is 1/2 to 2/3 of the cost of the whole system. And yet it really doesn't get the attention it needs. And so I want to give you some insights on that and some things that we've learned. So first off is duct sizing. And I've got on the screen there is a ductilator. You can also get apps that are pretty easy to use. And basically what you're putting in there is your duct dimensions. And you've got 3 different types of duct orientation. You've got round, oval, or rectangular ducting typically. So you would put in your duct sizing, and then you would put in your airflow, and the ductilator or the app will determine what your static pressure is going to be in that duct system. And it's done per 100 feet of duct. So typical is shown there on the screen is 0.08 inches of water column per 100 feet of duct. That's a target for a typical design to accomplish in a duct system. So what you'll find if you play around with either a ductilator or a duct app is that if you reduce the size of your duct and keep the volume the same, then you'll see the static pressure will definitely increase and you'll have more resistance in the duct. So having it sized right to allow for the airflows that you're designing is very important. As I said, there are different orientations. I'm showing here a rectangular. In some cases, you'll use a rectangular duct that's got a low profile where you've got a limited plenum in the ceiling, for example. You're going in above a drop ceiling and there's not a lot of room. A round duct won't fit, but a rectangular, so call it wide and shallow rectangular duct would allow you to get in through spaces and so forth. Same with oval ducting as opposed to round duct. He's asking if you have a separate heating and cooling system in DOAS is variable volume, you need to couple and balance these 2 systems. No, that's the advantage here, is that the heating and cooling system is its own and going to be providing its own balance. And the DOAS is providing, if it is properly done, it's a balanced system. So it's independent of that. Variable volume is going to be consistent on both the supply and return for the ventilation component. So the heating and cooling, by decoupling those and having them separate, you eliminate the need for having to couple them and balance them. So it's an actual advantage and makes life simpler. If you need anything more, Vlad, and more detail, I can expand on that. All right, so back to here with the ducts. You've got a situation where you'll have different configurations. And again, round, for those that understand what volume to surface area, it's kind of like the old tomato soup can. You know, the Campbell's soup cans were designed to use the least amount of metal for the volume that they hold. So it's round will allow for, if it's got the least amount of metal, it also has the least amount of surface area, so for volume. So round ducts are the most efficient. Now we get into fittings that go into a system, and this is where it gets really critical. And we'll see here, basically what they do is they say, okay, this is an elbow, radius elbow, and we're using 12 by 12 round or square ducting at 800 CFM. This is just consistent through these different examples I have. So this elbow is curved. It's approximately equal to 13 feet of ductwork for one of these elbows. And you may have many of these in a duct design system. And so these will all add up to feet of duct. Now, if you put in a square mitered elbow that's just a straight mitered elbow, that's an equivalent of 63 feet of ductwork. So what that means is you're going to have a lot of turbulence. This air coming down here is going to run up against this wall and create a whole lot of turbulence, and turbulence equals static pressure drop, and going to be a big factor. This is more curved, and so it flows more around. If you add in this same elbow vanes, turning vanes, you can reduce it to less than 6 feet of ductwork, which is really a huge factor. That's going to be less than half of this rounded radius elbow, 10 times less than the regular elbow for mitered elbows. So these can all add up to, again, if you have 20 of these in a system, it's 120 feet equivalent here. It's 1,200 feet equivalent here. And it's 260 feet of equivalent here. So it's a huge factor in the kind of components that you use in a duct system. And remember, if we're looking at this system, this is going to be there for a very long time. This could be in the building for 50 years, providing the ventilation. The HRV, the ERV will last 20 to 25 years. The ductwork's there, we call it forever. And so every day that the air is running through this ductwork, if you have to use more fan power to get it there because of the resistance you're creating here, then you're using more power, you're using more energy, and that whole system loses its efficiency. So these really become important. Now we look at where we've got takeoffs, T's and so forth. A straight T is equivalent of 50 feet of ductwork. A branch T, so this has got a little branch here that allows for easier flow. That reduces that in half to 25 feet. And a conical Y, everybody can see that. That means that the airflow is going to be much easier, is equivalent to 13 feet. So a fraction of just a straight T, and well, it's about half of the static that you'll have in this. Aubrey and I have been meaning to and intending to come up with a whole comparison between what we call first and worst on these systems. What if you used all of these, and all of these, as opposed to using these and these in a system? What would the difference be? And it can be dramatic as far as the equivalent ductwork length for a whole system. Air sealing is very critical in ducts, and there's a couple of interesting things here. One factor is what we call line of sight duct sealing. You can imagine the guy that's pictured there. Does he get the seam all the way to the top of that duct? It's always a concern of ours. If you can't see it, does it get done? So that is definitely a factor. It depends on when this is put in. Retrofitting ductwork into existing buildings can be extra difficult because there may be a drop ceiling that you're working around and working through, and there may be other mechanical piping, wiring, other factors that are playing a part and make it more difficult to do. So it takes a very comprehensive approach, but it really adds up to being important on the ventilation side. I have had people say, well, it's ventilation, it's going to be introduced into the building anyway. It may be up in the ceiling, but you're still getting the ventilation into the space. The problem is, if you're losing along the way in a duct system, by the time you get to the far end of the duct system where you put a hood on it and you say, okay, I need 150 CFM into this meeting room. Well, if you've lost 50 or 100 CFM along the way to leaks in the ductwork, then you have to run your HRV or ERV at another 150 CFM or 50 or 100 CFM, whatever the losses are. You're going to have to increase your total volume moving through the ducts to get to those far end spaces and provide the ventilation correctly to those spaces. So being effective in the ductwork is important. Another thing you can use that's very effective, and we recommend in a lot of cases, especially where we're doing retrofit work, is to use Aeroseal, where they come in and they put a polymer into the duct and pressurize the duct. They seal it all up, pressurize it, and the polymer finds all the holes. And it can seal up to a 1/2 inch gap, which is very significant. And by doing Aeroseal, you basically seal all the ducts virtually as tight as they could be, and then your system is very effective. So sealing is important. One of the funny things is, there's this tolerance for, well, we only have 15% duct losses, that's low. And the last point you'll see on that slide, and this was at Building Science Summer Camp, Joe Stiebrick's camp. He had a guy talking about, he was a ventilation, sheet metal installer, and talking about the importance of it. And he said, hey, what's the tolerance for leakage with plumbers? Well, if plumbers is 0, because it has to be, why can't we do better with ducts? And that's a good question. It's because air is, call it invisible. Air leakage is virtually invisible, and until you measure the airflow, you don't know what's happening. And so they don't worry as much about it. And it doesn't damage things. It doesn't, a water leak is going to destroy stuff. So it's a little bit different thing. Now, we do deal with fire and smoke dampers. They all have their own ratings for static, and you'll be able to put those into the formula. I don't want to spend too much time on it, but fire and smoke dampers are definitely something in code, especially in commercial, and have to play a part in the design. One of the things I want to stress is that how you put a system in will determine how many of those fire and smoke dampers. Typically between floors, you'll have to have a damper. So if you've got a 5-story building, every time you pass through a fire rated floor, you have to put a fire smoke damper in. So you may have 5 of those to get from the top, from the roof to the floor at the bottom. And that's all going to add up. So we talk to people about duct design, say, well, do you want to put a vertical chase and a vertical duct passing through all those fire and smoke dampers, or do you want to put in an HRV or an ERV on each floor and do the building per floor, and then you eliminate all those fire and smoke dampers? One thing you have to remember is, because these are mechanical systems, they have to have a hatch. Not only do you have to put the duct or fire and smoke damper into the duct system, but you have to have an access hatch where people can service it. So if you have 5 of these vertically on a duct, you have to have 5 hatches in the ceiling or in the wall or whatever to give access to where that fire and smoke damper is to service this. You see mechanical. So that's added cost. They can add up on a total construction cost. So that's where looking at duct design can have some payback. Caleb asked about fire dampers and Aeroseal. Typically they cover them. So they would figure out, again, that's where you have access to it, and you try to cover that up so that it doesn't get, but to be honest, I don't know overall. I'd have to ask Aeroseal about that. I'm not sure. Probably worthy of a question for them. I think they probably open them, leave them open, and so the Aeroseal would not tend to try to seal as long as they were fully open. But Caleb, I don't know the full answer to that, to be honest, and I'll need to contact my Aeroseal contacts and see what they do with those. That hasn't come up. Thanks for the question. My guess is if they're open, then there isn't a area where they would try to fill a leak if there's not a point there. And then I just mentioned acoustics and vibration dampers. Depending on what your system is, it's interesting. I've been doing this a long time, with first in residential with Zender and now with Ventacity. The motors and fans that we use, the ECM motors and fans, have virtually no vibration. They're extremely stable. And so having, I think it depends on the equipment you're using, whether you use vibration dampering. Sometimes they require it in code, and in fact, code in my mind just hasn't kept up with technology, where it's really an unnecessary and potential an issue. This is basically a vibration damper where this is oftentimes almost like sealed canvas, and it allows for, it will not transfer vibration from this unit into the ductwork. But if this isn't stretched fully tight and well installed, it can actually be something that's going to create turbulence and noise. And I saw this in my Zender days with some residential units where this damper, this acoustic or vibration damper, was kind of bunched up and causing all sorts of turbulence in the airflow and actually making noise. And I said, just take it off. We don't need it, because our ECM motors and our units are totally vibration proof. They do have silencers, and they're very effective depending on the application, and they can be installed fairly easily. Again, any of these where you have restricted flow going through a acoustic damper is going to create some static, and so you have to figure that into the conversation. So this is a thing that we run into once in a while. So what you'll see here is, this is on a roof in Seattle. So this is the HRV, and here's where the penetrations are to go into the building supply and return. And it was baffling that they would do this, because what you've got here is 190, 290s, 390s, 490s to get this supply air into the building. And then your exhaust has 1, 290s, and totally unnecessary. And this is insulated duct, but it's still on the roof. It's Seattle, so it's a little temperate, but potentially it's gonna have an influence on the efficiency of the system. And I'm gonna talk about that shortly in the next example I have. The other thing is that you have to either crawl under or crawl over these ducts to get at the access here this is where the door for the filters are. So you got a service on the roof crawling under a duct to get at it. It was just crazy. The reality is all you had to do was put it on a curb right here. The bottom, these duct out the bottom, not just out the ends, you can duct it out the bottom. This thing could be moved right here and ducted directly into the building. Insulate those very short ducts, could be significantly insulated, and you have no 90s and no duct that the air is moving through. You would have eliminated a lot of static and just a simpler system. We were just dumbfounded when we saw this. That's what happens when you take your eye off the ball. And this is one in Portland, Maine, which there was a curb over here with a rooftop unit, but we wanted, it was needed to come in with the ducts into the building and supply and return here. This is a total of over 30 feet of duct. And this is on the roof in Portland, Maine. And so at 10 below zero, when I saw this, the tenant on this project sent me a text with this picture. And my immediate reaction was, well, what you got there is a Prius with a 10,000 pound trailer. And you think you're going to get 50 miles to a gallon. And it just isn't going to happen. If you think about this, okay, this is your supply air, and this is your return air. Oh, excuse me. No, this is supply. Yeah, this is your supply air. Or excuse me, this is your return. This is coming out of the building, and this is the supply going in. So you've got a situation where if you've got 70 degrees leaving the building, it's going to be 69, 68, 67, 66. These are insulated, but they're insulated with like an R8 modest insulation. And again, if it's 20 below zero, so now we've went from 70, by the time it gets to the ERV, it's 66. Even at 90% efficient, it's 20 degrees outside and we're leaving at 70, coming in at 66. What's the best we're going to get? Or leaving at 66, excuse me, from here and coming in at 20. What's the best I'm going to do? 64, 3, 2? It's heat recovery. If it was 70 degrees going out, we'd be at 67, 66, 67. If it's 66 going out, now we're down to 62, 61, 62, 63. What a huge difference. So we're in a situation where all this ductwork was a real problem, not to mention 90, 90, 90, 90, 90, 90, all those turns, all that ductwork, just crazy. So that's what it looks like now. So we had a meeting on the roof and we said, okay, this is a insulated curb, call it, plenum, and then insulated directly into the building. No ductwork on the roof, very short, between 70 degrees coming out is going to be right at the unit, 70 versus now we've got optimum efficiency. And we had to do a little work on cleaning up where they had the ducts on the side and so forth. Caleb just threw out a little thing where if this is your exhaust and this is your supply, they say you have to have 10 feet of separation. It's somewhat ridiculous, and we've never had this challenged where basically you're saying you got to put a extension out here with a duct so that you separate them by 10 feet. if you're blowing out this way and you're pulling in over here, I've not yet had a code officer say this is any kind of an issue, and yeah, we'll see. But to date, we haven't seen that as a problem. So one of the challenges we have in this world is the change order, and it's the enemy of the good sometimes. And this is just an example of that. You know, there's a lot of boats named change order, which tells you everything. There's a lot of money in change orders. You know, I just Googled change order boat and got hundreds of hits. I think this one on the right here, for those that can read that, this one takes the cake. This is original contract is the dinghy, and the yacht is change order. So a lot of you are probably laughing out there, but we are seeing this when we are doing these projects where, you know, those rooftop duct designs, you know, I'd say that these guys made a lot of money, you know, charged a lot of money for all this duct work when it could have been just like that. What a difference. And then you got this one. I think he's probably works for, you know, does contracts with the city of New York, or, you know, maybe the New York City School Construction Authority does their HVAC or something. And that is for today about all I've got, and take questions. You can unmute yourself, I think. I'm not in control because I'm not the host, but if you'd like to unmute and ask any questions or throw it up on chat, feel free to do so. Anybody?
Those examples were, you know, they were kind of nuts. I mean, it's like, what were they thinking? I mean, I know we have certain difficulties, like in New York City, you can't put units like this on wood framed roofs or light gauge metal framing. They have to be either on walls, or so there's a limit.
Yeah, you have to have an engineer, and they need an engineer to.
Yeah, and you need to put in, you know, dunnage and stuff, or you can mount things to walls, but generally when you're doing units like this, it's not a problem. So it's just like, did you get an explanation of why the project in Portland that you changed, like they put that much ductwork on the roof?
There was a curb where they ended up putting the unit, and so they could just slap it on the curb, and they just weren't really thinking. And said, yeah, well, we'll just throw it on this curb right here instead of dealing with a stand and potentially having to get an engineer to sign off on putting it where they put it. They just said, well, we got a curb, we'll throw it right here. We don't have to do anything. It's easy.
Yeah, that probably was it.
Yep.
Yeah, the only thing that we had an issue with, the project never happened, but we were close up against a parapet. So we actually just raised the curb up to the level of the parapet and put the unit on top of that. And it actually would have made it really easy for the installation and any kind of servicing of ductwork later on.
Yeah.
So.
Yep. Believe me, I've seen all sorts of things. Those are just two examples. I don't like to dwell on it, but we've seen, you know, undersized ducting. We've seen where they you know, they got up against a beam came across, and so they only had 4 inches to go over it, and they just put in a small, totally undersized run of duct to go over it. And it's like, holy cow, that's just not going to work. So, you know, you run into things all the time, and sometimes you have people that are conscientious, and sometimes you have people that are just, I think it's a lack of, call it education and knowledge about the impact. I think very few people think about the impact from an energy perspective on duct design. It's
Yeah.
really about, well, just getting enough air to where you need it. But nobody really thinks about, well, static and increasing static pressure or resistance in ducts translates directly to fan power in delivering the air. And so that's an important thing that, I think is not understood or appreciated by the people that are installing the ductwork. They just get a set of plans. They say, okay, I'll put this in. And then when they run into something in the field, which is totally, understandable, there are things that are in buildings, especially retrofits, but even in new buildings, there are things that happen that weren't on the plans. Yep. It didn't talk about that beam that went across, or the plumbers got there first.
Yeah.
and there's a pipe running through there. There's a large, drain pipe, or any number of things that.
Drake has a question. How often do the ducts need to be cleaned, and what kind of methods?
Yeah, in our typical system, and with a heat recovery ventilation systems, you're going to have filters on the exhaust as well as the intake. So as far as exhaust ducts getting dirty, it's usually not too bad. The intake duct, hopefully it's already gone through the HRV, which has a very, in our case, MERV 13 minimum filter. So as far as the ducts, they shouldn't get a lot of contamination, but I would recommend inspecting them on a yearly basis to just get a visual inspection, and then take it from there. I don't think there's a set time. It shouldn't be that there's a whole lot. Anything that does get through the filters, either on the supply side or the exhaust side in the ductwork, should end up just passing through, and you're not going to get a lot of nasty stuff. Sometimes on the exhaust side, on where you're exhausting out of a space, you're going to pull, there could be grease or oil if it's too close to in a kitchen area or something. There can be some things on the exhaust side ducting, and again, you inspect it. And then there are professional duct cleaning companies that go in and have brushing systems that go right through ducts and do it pretty readily and easily. But I think a yearly inspection is a good idea, just to take a look in the ducts, and that's usually done. Remove a exhaust grill, for example, and then just pop up and with a light determine what the ducts look like, and take a peek.
Yeah, that's always been my concern with the internally insulated ductwork, because that insulation on the inside doesn't really.
I don't recommend it at all.
Yeah, exactly. It's like always like when engineers.
It can down on the insulation.
Yep.
Yeah.
And it's a fiberglass insulation. So what is that putting into the air system?
Yep.
So yeah. All right, I think, unless anybody else has any other questions, I think we thank Barry, and we'll go on our merry way.
And we've got another one coming up on.
Oh yeah, when is that?
The 13th and the 27th. So the 13th of October. HVAC retrofits on the 13th. And that's going to be a really good one, because that's really pertinent. And, we're going to talk about energy efficiency requirements in New York City specifically. And I'm going to talk about passive house interfit and, retrofits. And I'm going to talk about projects we've done and some amazing case study work and data and so forth, and a solution. And I think that'll be really interesting. And then the last one on the 27th is about applications. So we're going to talk specifically about multifamily ventilation, about offices, about schools, different types of buildings, retail, and give some insights into approaches to do ventilation in those spaces. So that's the next two.
Great.
All right.
All right. Thank you, Barry.
Thank you, everyone. See you for the next one. Have a great Tuesday.